And hello, welcome back to this video series on boundary layers, laminar boundary layers. So in the last video we were talking about some of these scaling, and we want to say that the idea is to convert all of these equations into the dimensionless form, this u star, x star, y star, so that you can have a proper comparison of terms. So the idea is that we have all this u star, y star, etc. All should have the order of magnitude of 1, so that we can do some easy comparison. Okay. Okay. So next thing, we already went through how to scale. Okay. Oh, this is a big wrong y. It's a capital Y. So u star, y star all should have this order of magnitude of 1. Okay. Some people use prime or plus or whatever. The important thing is that you know what all these physically mean. Okay, doesn't matter what the notation is. Okay. Anyway, we were talking about how to scale the x velocity, which is u, and now u star is the x velocity divided by the free stream velocity. That should give you a proper non-dimensionalization such that this should be on the order of magnitude of 1. Do the same for the x length scale. Should be on the order of magnitude of L, which is how far you are going into the plate. And of course the y scale is scaled by the boundary layer thickness, the momentum boundary layer thickness. And how then are we going to scale the rest of our terms? Okay, so for example, how do we scale this v? Okay, it's not like random. We can actually apply this scaling straight into our continuity equation. So we can scale our continuity equation so that we can properly find what the y velocity scaling is, because we already scaled the x velocity, we scaled the x length scale, we scaled x velocity, and we scaled the y length scale. So let's substitute all these into all of these expressions into the what do you call that? The continuity equation. Sorry, the continuity equation. So I'm just going to start writing as it's compiling. So over here, at the bottom you will have x, right? So x is actually x star into L, and u is actually u star into u infinity. So the same we can do for the y side, the y length scale and the y velocity scale. But the y velocity scale, we don't really know what to do with it yet. Alright? But sooner or later things will become pretty apparent. Okay, so let's first factorize out the constants. The constants here are L, u infinity, and delta p, which is the momentum boundary layer thickness. These don't actually, L does not vary with so-called x. This is just where we are in our how far we are going, how long the flat plate is. And u infinity doesn't change with x as well. U infinity doesn't change with x. The free stream velocity doesn't change with x. And of course, the momentum layer thickness, while it does change with x, it doesn't change with y. So we can actually factorize that out as well. So let's do this. Okay, I'm going to do some editing of the equations. Okay, so u infinity should be in the numerator, L should be in the denominator. So this is what it should look like once we do the compiling. Of course, I can factorize this thing out here. Okay, 1 over delta p, and that's how we can start to see what the v velocity scaling should look like. Okay, so now we have this. Let's see. We can actually divide throughout by this u infinity over L. So we multiply, it's the same as saying we multiply the whole equation by L over u infinity. Alright, so let's multiply by L over u infinity, and let's get rid of this front part and get rid of this. So okay, and I think this u, the plus should not be a superscript, it should be actually a plus. Okay, so now you can start to see, okay, alright, forgot, I think there's a u star there. Now the thing about, again, the thing about all this, the way we scale, we do scaling, we know that x star is on the order of magnitude of 1, u star is on the order of magnitude of 1. So in fact, this whole term here should be on the order of magnitude of 1, right? This, again, I'll say, u star and x star are both on the order of magnitude of 1. So this whole term here should be on the order of magnitude of 1. And since these two are the only terms in the equation here, we can say that this whole term here is also on the order of magnitude of 1. And we know that y star is also on the order of magnitude of 1. So we can say that v times L over delta p u infinity, that should also be on the order of magnitude of 1. Okay, so we can define, we can say, okay, so VL over delta PU infinity is equals to order of magnitude of 1. And let's compile that. So we can actually define, okay, I used the wrong O. We can actually define this to be our V prime or V star. I'll call it V star. Okay, so V star will be equals to all of this. So how we scale V is using this delta P u infinity and L. Okay, so we can of course make it look a little nicer by bracketing every of these terms together. Okay, you can bracket every of these terms together. So it's u infinity delta p over L. Okay, and that will give you, okay, so this will give you the proper scaling. And of course, we can just change this whole thing to V star. Okay, if we substitute this expression back here, okay, we will get the following. We will get this whole thing disappear, and then we'll just have del u star, del x star plus del v star, del y star equals to 0. This looks exactly like the earlier continuity equation. Where is that continuity equation? Yeah, this looks exactly like the continuity equation we are doing earlier. However, of course, we specified how v and everything else should be scaled so that everything works. So these two are here. We don't cancel any of these terms here because they have to like hold. Alright, what else? Okay, what else? Okay, so now we will actually have to do something else to this Navier Stokes equation as well. Yeah, we will have to do something else to this Navier Stokes equation as well. And one thing we need to do is get rid of this. Not get rid of this t. we have to scale t properly. Okay, now we move on to the Navier Stokes equations. So we need to scale the time. Alright, so we need to scale the time. So what's our time scale here? Okay, the time scale, well, since we already have a length scale and a velocity scale, the length scale is equal to what? L, the x length scale, and the x velocity scale equals to u infinity, right? So we can also say that the time scale it will be equals to just, you know, distance and time. You know, you just do your multiplication. Okay, you just do your multiplication and that's it. So what you do, L over u infinity. Alright, and that will give you your time scale. Okay, maybe I should like center it, but let's see. Yeah, but this is basically how you would do it. Okay, the time scale can be so-called given as such. So let's do t star. Okay, we're going to do t star equals to t over the time scale, which is this over here. So it's t over the time scale, which is here. Then yeah, that's how we scale time. Okay, next thing we need to do is so-called have our pressure scaling, but you know, the pressure scaling we have not quite figured out how to do it, and of course the gravity scaling we have not really figured that out as well. However, yeah, we will see what we can do about that later. But first thing first, let's copy all of this down. Okay, let's put all of this into the Navier Stokes equation. All this scaling. Let's scale the Navier Stokes equations, which is the boundary. Momentum. The momentum equations. Okay. So these are momentum equations in 2D. We'll need to scale them accordingly. So it's going to be a little bit tedious, so do bear with me. We'll need to start replacing all of our u, the x and the y. All of this will need to be replaced accordingly. There's no like shortcut here. You'll have to do it. Okay, so we'll need to do the x momentum equations first. Okay, x momentum equations. Alright, so let's start with this u. This u will be u star into u infinity. Alright, so let's see where I can copy and paste all of this. So we'll need to do many times. U star u infinity here. Then I'll try to just replace every single bit of that. Okay, this one here and this one here. The rest should be okay. Next thing I'll need to do is actually scale this x. Okay, x will need to be changed into x star times L. So remember, we were scaling the length, the x coordinate by this x star by L. So x equals to x star into L. Alright. As you can see, it's getting more and more messy. Okay. So that's the u part. It's going to get very, very long. I have not finished with the x part yet. However, there's one thing we can do. You can see that u infinity is almost on all of these what do you call that, units and what have you. One easy way is to divide everything throughout by u infinity. Okay, so u infinity will be divided throughout here, 1 2 3 4 5, and then of course we'll have to divide the right hand side by u infinity as well. So that will make it a little bit neater. So let's do 1 by u infinity. So I'll just get rid of u infinity. 1 2 3 and 4. So hopefully I don't make any careless mistakes here. Okay, so that's the first round of division, because over here you still have one more. Okay, I should delete that one as well. This shouldn't be here. Okay, we are more or less there. Okay, and you'll notice we still have one more u infinity to actually deal with. Okay, I mean one more u infinity, because over here we have another u infinity there. But okay, that's what we can actually do for now. All right. Let's see what we can do next. The next thing we can scale is this x coordinate. So this will be x star into L once. This one will be x star into L twice, because this is del by del x squared. So let's do x star squared, and then we'll bring the L squared out. So nu will be divided by L squared. Okay, so I'm just dealing with this term here. What do we do with y? Y, we can scale it by the momentum boundary layer. Okay, so I'm bringing this out here. Y we can scale by the momentum boundary layer. Okay, so let's do that for y. So y star, and same procedure. We'll just bring it out, the extra little factor there. Okay. So we'll just bring out the delta p factor there, and let's see. Okay, same, and then we'll do the same for this part as well. Okay. Oh, okay. One more thing I kind of forgot is this little x squared here, or this little x here, which that also needs to be scaled. So I'll do the x star scaling. Now bring the L outside. Okay. So that should about do it. Alright, so that's our equations partially scaled. Okay, I think I made a mistake here. This should not be outside the bracket. This should be inside the bracket. Alright. Alright, so so yeah, now we are starting to see a little bit more of neatness, so to speak. Okay, next thing we want to deal with. Okay, we want to deal with this v velocity thingy here. Okay, we want to deal with this v velocity. Okay, of course we got to factorize these two out also. So we can factorize out the L and we can factorize out the u infinity. So let's just tidy up the equations before we continue. Okay, so u infinity over L. Let's get rid of the L inside and the u infinity as well. Okay, so that's that much we do with these equations. All right. Oh man, that was tedious. Okay, so again, it looks like we can start considering whether to use this to divide throughout, and I think we can do just that. Then we'll need to scale time. Fortunately, I think probably running out of time for the time being, and I think we may stop for now. I don't want to carry on. I think the last few videos were like 20 plus minutes. I normally try to keep it within 20. So I'll just stop for now. Let's continue this in the next video.